Hello everyone, I'm Kavita from the Department of Artificial Intelligence and Data Science, Ramco Institute of Technology. In this lecture, we will know the fundamental concepts of transaction in database systems. Understanding transactions is crucial for ensuring the reliability and integrity of our data, especially when multiple operations are being performed concurrently or when system failures occur. We will explore what a transaction is, the critical properties it must satisfy, the different states it goes through, and how we manage the execution of multiple transactions. So, what exactly is a transaction? A transaction is a unit of program execution that accesses and possibly updates various data items. Think of it as a sequence of operations that are treated as a single logical unit of work. So here is an example transferring rupees 50 from account A to account B. And this involves several steps like reading the value of A, and you have to reduce 50 from A, and then you have to write the value of A. Again, you have to read the value of account B, and then you have to increment it value by 50, and then you have to write the value of B. So these are the steps involved in this simple transaction. All these individual operations work together, form a single transaction aimed at achieving a specific goal. When dealing with transactions, database systems face two main challenges. So there are failures of various kinds, such as a hardware failure and system crashes, and concurrent execution of multiple transactions. To address these challenges and ensure data integrity, transactions must adhere to a set of properties commonly known by the acronym ACID, which means atomicity, consistency, isolation, and durability. Let's look at each of these in detail. First thing, atomicity. Atomicity means that either all operations of the transaction are properly reflected in the database or none are. In our example of transferring rupees 50 from account A to B, if the system fails after deducting rupees 50 from account A, that is step 3 here, but before adding it to account B, step 6, the money would be lost, leading to an inconsistent database state. The atomicity requirement ensures that if a transaction cannot complete fully, any changes it has made are rolled back, and the database remains in its original consistent state. And then the second property is consistency. Consistency ensures that execution of a transaction in isolation preserves the consistency of the database. This means that if the database starts in a consistent state, any transaction will take it to another consistent state. In our example, it states that the sum of A and B is unchanged by the execution of the transaction. Consistency requirements can include explicitly defined integrity constraints like primary and foreign keys, as well as implicit constraints. It is important to note that during transaction execution, the database may be temporarily inconsistent, but it must return to a consistent state upon successful completion. Erroneous transaction logic can lead to inconsistency. And then isolation. Isolation deals with the concurrent execution of multiple transactions. It dictates that although multiple transactions may execute concurrently, each transaction must be unaware of other concurrently executing transactions. Intermediate transaction results must be hidden from other concurrently executed transactions. Uh, if a transaction T2, so consider this example T1 and T2. So T2 reads the accounts between steps 3 and 6 of our transfer transaction, that is T1. It will see an inconsistent state where the money has been deducted from A, but not yet added to B, leading to an incorrect leading to incorrect sum of A plus B. For every pair of transactions Ti and Tj, it appears to Ti that either Tj finished transaction or its execution before Ti has started, or Tj started execution after Ti finished. While isolation can be trivially achieved by running transactions serially, one after the other, executing multiple transactions concurrently has significant benefits, such as increased processor and disk utilization and reduced average response time. And next thing is durability. Durability ensures that after a transaction completes successfully, the changes it has made to the database persist even if there are system failures. Once the user is notified that the transaction has completed, for example, the rupees 50 transfer has taken place, like in this example, the database updates must survive any subsequent software or hardware failures. So these are all about the asset properties of a transaction. And so these are all the various definitions of the properties. And next thing is transaction states. So a transaction goes through several states during its execution. Initially active, and then partially committed, failed, aborted, and then committed. So see this example. So this is a state diagram of a transaction. So it depicts the various states. So initially active. So this is the initial state where the transaction is executing, and partially committed, the status reached after the final statement. Listen, after the final statement of the transaction has been executed. And then failed, this status entered after the discovery that normal execution can no longer proceed, possibly due to an error. So in case of error, it will move to the failed state. And then aborted state, after a transaction fails, it needs to be rolled back, meaning the database is restored to its prior state, that is, state prior to the start of the transaction. After being aborted, a transaction can either be restarted or killed. Restarted means if there are no internal logical errors, it can be restarted. And the final state is committed. This is the state after the transaction has successfully completed. So these are all the various transaction states. And then we will see about concurrent execution. So as we briefly touched upon, database systems often allow multiple transactions to run concurrently. This offers several advantages, including increased processor and disk utilization, leading to better transaction throughput. For example, one transaction can be using the CPU while another is reading from or writing to the disk. So that is better transaction throughput as well as increased processor and disk utilization, reduced average response time for transactions. Short transactions don't have to wait behind long ones. To manage this concurrent execution, we use the concept of schedules. A schedule is a sequence of instructions that specifies the chronological order in which instructions of concurrent transactions are executed. A schedule must include all instructions of the participating transaction and must preserve the order of the instructions within each individual transaction. So there are two types of schedules. We will see it one by one. Serial schedule as well as non-serial schedule. In serial schedule, transactions execute one after the other. So see here like this. This is a schedule with transactions T1 and T2. This ensures consistency because each transaction runs in isolation. Consider this example with the two transactions T1, which is transferring rupees 50 from A to B, and T2, which is transferring 10% of the balance from A to B. So a serial schedule would be either T1 completely followed by T2 or T2 completely followed by T1. A serial schedule is inherently consistent. So this is an example for a serial schedule, which is there is T1 followed by T2, and it can also like T2 followed by T1 like this. And the next one is non-serial schedule. A non-serial schedule is one where the operations within the transactions are intermixed. So see here like this. In this example, both the transactions T1 and T2's instructions are intermixed. While non-serial schedules can improve performance, they can also lead to inconsistencies if not managed properly. So in this example, a concurrent schedule that does not preserve the value of A plus B, highlighting the potential for problems. So this preserve the value of A plus B, even if the transactions are non-serially executed, it will preserve the property sum of A plus B, and this schedule does not preserve the value of sum of A plus B. So to achieve isolation in this is an example or a diagram for the classification of schedules. So to achieve isolation in concurrent schedules and prevent inconsistencies, database systems employ concurrency control schemes. These are the mechanisms to control the interaction among the concurrent transactions in order to prevent them from destroying the consistency of the database. Finally, it's important to note how the transactions conclude. A transaction that successfully completes its execution will have a commit instruction. So see here in this example, we have mentioned commit. It will have a commit instruction at the last statement. By default, it is assumed that a transaction executes a commit instruction as its final step. And conversely, a transaction that fails will have an abort instruction as its last statement. If it has failed means we have to include abort instruction as the last statement. In a summary, transactions are fundamental units of work in database systems that ensure data integrity through the asset properties, that is atomicity, consistency, isolation, and durability. Understanding the different states of a transaction goes through and how concurrent transactions are scheduled is crucial for building reliable and efficient database applications. Thank you for your time, and I hope this lecture has provided you with a solid foundation in transaction concepts. Thank you.